Hello everyone, this is lecture 24 of the subject analog circuits. In this class, I am going to discuss op-amp design and frequency compensation. So, in the last class, I had discussed the concept of stability and also I had discussed multi-stage amplifier, that is lecture number 23. So, in multi-stage amplifier, what happens when we require higher gain? Then the single stage amplifier, it cannot provide that particular gain. For example, if we require 80 dB gain, 90 dB gain or more than 100 dB gain. So, we cannot achieve it with the help of single stage. So, to get such gain, we connect single stage amplifiers in cascade, and when we connect single stage amplifiers in cascade, then the overall gain, it becomes the multiplication of the gain of the individual stages. For example, this is the structure of the two stage amplifier. Let us say the voltage gain of the first stage is AV1 and the voltage gain of the second stage is AV2. Input signal, it has been applied at the input of the first stage and we are taking the output from the output of the second stage, that is V naught. So, when we calculate the overall gain of this two stage amplifier, then the overall gain, let us say it is AV, it is equal to AV1 into AV2. So, this is the two stage amplifier kind of multi-stage. Similarly, for 3 stage amplifier and for 4 stage amplifier and more than for 4 stage amplifiers, we can get higher gain, right. So, but normally we are limited to second stage, 2 stage amplifier, 3 stage amplifier or up to 4 stage amplifier, because as the number of stages increases, then the number of comparable poles and zeros also increases, and that is a great threat to the stability, and at the same time the bandwidth is also reduced for the higher stage amplifiers, right. So, in multi-stage amplifier, we connect single stages amplifier in cascade to get the higher gain, right. So, now I am going to discuss how we can design this multi-stage amplifier, that is a kind of op-amp design, right. So, that operational amplifier is a kind of multi-stage amplifier. So, starting with the op-amp design, basically in op-amp we are having, normally we are having more than one stages, right. The first stage, it is always a differential amplifier, that is the first stage, that we can say it is a input stage. The reason is that the first stage is the differential, then the effect of noise will be less, because it rejects, this differential amplifier, it rejects the noise will not be propagated to the second stage and third stage. That is why normally the first stage we design, that is the differential amplifier, and after that to get higher gain we can connect an additional stage at the output of this differential amplifier, that is the second stage. So, we can use this second stage for example, CS amplifier, common source amplifier, right, to get the higher gain. Then we can further connect one more stage, one more common source amplifier if we want more gain. Otherwise, we can connect the voltage buffer, that is also called voltage follower, at the output. So, this output stage, it is in general the voltage buffer stage, voltage buffer or voltage follower. So, this voltage buffer or voltage follower, it is basically the common drain amplifier, that is also called source amplifier, when we are designing it using MOSFET. When we are designing it using BJT, then it is common collector configuration. So, in operational amplifier, the general structure is, the first stage is the differential amplifier to reject the noise, The second stage is common source amplifier to get higher gain, and normally the output stage is the voltage buffer stage, voltage follower stage. The reason is the output impedance of the voltage follower is very less. Output impedance is very less. So, the advantage of using this voltage follower at the output is to minimize the signal loss. It also minimizes the loading effect, right, that I had discussed in unit 1 when I had discussed common drain amplifier. There I had discussed the role of this voltage follower. So, in general this is the structure of this operational amplifier. So, starting with the design of CMOS differential amplifier with a current mirror load. So, in differential amplifier, that differential amplifier it can use the passive load also like resistive load, or it can use the active load like current mirror that I had discussed in the differential amplifier class, right. So, firstly I am going to take a differential amplifier circuit, and for that circuit I will discuss that how we can design that differential amplifier. So, differential amplifier with current mirror load. Current mirror load means it means that we are going to use the active load, fine. So, it is a differential amplifier, it means that the input signal will be differential, and that input signal it will be provided, it will be given to the gate of two transistors. Let us say these transistors are M1 and M2, right. Since it is a differential amplifier, so the input signal is the differential input, this is your Vin. So, the input signal it has been applied in between the gate of M1 and M2, right. To bias these transistors we need to connect a current source also, right, or we can connect we can design that current source using transistor also. This is, let us say it is transistor M5. This transistor M5 it can act as a current source if we apply a certain bias voltage at the gate of this M5, right. So, since the current mirror it is acting as a load, so let us consider a PMOS current mirror. So, PMOS current mirror, in the PMOS current mirror the source of both the transistors means let us say it is M3 and M4 transistor, it is connected to the supply voltage VDD, right, and the drain of M3 is connected to the drain of M1, and the drain of M4 is connected to the drain of M2. Since M3 and M4 is to be current mirror, it has to be formed current mirror. So, the gate of M3 and M4 will be shorted and M3 should be diode connected. So, if the M3 is to be diode connected, it means that the gate and drain of M3 it should be shorted. So, M3 is the diode connected. So, this M3 and M4 transistor it forms a PMOS current mirror. M1 and M2 are the input transistors and M5 is the current source, right. We can connect a current source also, but this M5 is acting as a current source, and this bias voltage VB is applied such that by which this M5 it should be in saturation region, right. Now, this is the basic structure of the differential amplifier with the current mirror load, and we are taking the output from the drain of M2 and M4. Let us say we have connected a capacitive load CL at the output, this is the V naught. Now, we have to design this differential amplifier. So, whenever we have to design the differential amplifier, we design it for a particular specifications. So, those specifications should be given, or we assume some specifications, because we need some specification, for that we design a particular amplifier. So, basically we have to firstly select the appropriate relationships between that connect the design specifications to the design parameter. It means that we have certain design specifications. To meet those design specifications, we decide some design parameters. For example, the design parameters are like W by L ratio, that is the aspect ratio for M1 to M5 transistors, and current in the M5 transistor, right, that M5 is acting as a current source. And the starting point of the design, it consists of mainly two information. The first one is the design constraint. It means that firstly we need to decide that at which technology node we are going to design the circuit, that is the technology, and we have to decide the supply voltage also, at which supply voltage we are going to design that amplifier, right. Technology means like it is a 180 nanometer tech node for example, then it means that the minimum dimension that we can take, that is 180 nanometer, normally it is referred as the channel length, right. Next one is specifications. Specifications, it can be anything. For example, for a certain voltage gain, for a particular frequency response, for a particular ICMR, that is input common mode range, for a certain slew rate, for a certain power consumption, for certain power dissipation, we are going to design a differential amplifier. So, these specifications it should be given. For example, if we are going to design a differential amplifier, then firstly we should know that how much gain we want from that amplifier, how much slew rate we want from that amplifier, and at what capacitive load we are going to use that differential amplifier, what power consumption we want. Obviously, we want lesser power consumption, but these things should be clear at the starting of the design. These are called specifications. Now, to meet these specifications, we decide the configuration of the amplifier, we decide the W by L ratio, right. So, let us see that how we can do it. So, the basic design procedure is, firstly, for example, assuming that the voltage gain AV is given, minus 3 dB frequency is given, slew rate, power dissipation, ICMR, that is input common mode range are given, these parameters are given. And obviously, we have to decide that what value of CL we are going to take, right. CL, that is the capacitive load, right. And if we write the design equations for this particular differential amplifier, then the voltage gain AV, it will be equal to the transconductance into output resistance of this amplifier. Slew rate, it will be equal to the current in the M5 transistor, the current flowing through the M5 transistor is I5 upon the load capacitance CL. The minus 3 dB frequency, it will be equal to 1 upon R out into CL. So, these are the design equations. So, this voltage gain equation, minus 3 dB frequency equation, we can derive it by doing the small signal analysis. Slew rate is related to the large signal analysis. Now, we have to firstly choose the value of I5. Since slew rate is equal to I5 upon CL, it means that, for example, let us say we want the slew rate of 1 volt per microsecond, right. So, that slew rate is given. We have decided some value of capacitive load, at what capacitive load we are going to design this differential amplifier. So, from this equation we can calculate the value of I5. If we know the value of the I5, that is the current flowing through M5 transistor. So, from there we can also find out the total power consumption. So, the total power consumption of this circuit, it will be equal to power consumption, it will be equal to, let us say power consumption is P will be equal to VDD into supply voltage into the total current drawn from that supply, that is I. So, if we are using single supply and the source of M5 is connected to ground, then the power consumption will be VDD into I. But if we are using dual supply, Dual supply means plus VDD and minus VSS. Then what will be the power consumption? The power consumption it will be equal to VDD plus mod of VSS into I, right, if we are using dual supply. So, from here we can get the value of power consumption, right, if we know the value of I5. After that we will check that what value of R out we require to satisfy the frequency response. From the frequency response we can measure the bandwidth, we can measure the gain margin, phase margin, and if we are not getting the particular frequency response, then obviously we will change the value of M5 to, or we can modify the circuit also. Modify the circuit means we can choose a different topology. Now, the W by L ratio of M3 and M4, it will be decided to satisfy the upper value of the ICMR, and we will select the aspect ratio of M1 and M2 transistor. W1 upon L1 is the W by L ratio of the M1 transistor. W2 by L2 is the W by L ratio of the M2 transistor. We will select the value of W by L for M1 and M2 to satisfy the AV, that is the voltage gain, and the W by L ratio of M5 transistor, it will be selected to satisfy the lower ICMR, and if we are not getting the particular specification, the required specification, then obviously iteration will be done. We will again change some value of the W by L ratio, we can change the configuration also to meet those specifications. So, the point is that to design this differential amplifier with the current mirror load, we need to know the total current flowing through the circuit, we need to know the W by L ratio of all the transistors. So, the W by L ratio of M1 and M2, it will be selected as per the voltage gain requirement. The W by L ratio of M3 and M4 is selected as per the upper ICMR range. The W by L ratio of M5 is selected as per the lower ICMR range, and the total current flowing through M5 transistor, it will be decided by the total the capacitive load at which we are designing the circuit, as well as the slew rate what we want from this circuit. So, this is the basic design procedure to design differential amplifier. Now, coming to the design of the gain stage and output stage. So, gain stage, for gain stage we can use the common source amplifier, and for output stage we use the voltage buffer. So, as far as this common source amplifier is concerned, so we can use the common source amplifier for, we can design this common source amplifier for different load conditions. For example, let us take the example of the resistive load. This is the drain resistance RD, this one is V in, this one is V naught, this is supply voltage VDD. The voltage gain of this resistive load common source amplifier is minus GM into RD. Minus sign is there because common source amplifier is the inverting amplifier, right. Similarly, another load condition is the current source load. In the current source load, what we do? We just replace this drain resistance RD with a current source. So, to connect that current source, to design that current source, what we do? We just select a PMOS transistor, we can select this PMOS transistor, let us say this transistor is M2, and at the gate of M2 we apply some bias voltage. This is the supply voltage VDD, and M1 will remain same, that is the NMOS, this is M1. Input is applied at the gate of M1, output is taken from the drain of M1 and M2. So, this particular circuit which consists of these two transistors M1 and M2, this is again the common source amplifier with current source load. M2 is acting as a current source, VB is the bias voltage, and the gain of this particular circuit is minus GM1 into RO1 parallel to RO2. GM1 is the transconductance of M1 transistor, RO1 and RO2 are the output resistance of M1 and M2 transistor. So, we can select any common source amplifier to get the required gain, and the gain value is given, that is given in the specification. So, to get that gain value, we can select the value of GM and RD accordingly. If we want to increase the gain, we can increase the GM, but if the value of the GM increases, then at the same time the current also increases current increases, it means that the power consumption will increase. So, there is a trade off, right. So, as per the value of the gain given, voltage gain given, to get that voltage gain, to achieve that voltage gain, we select the value of the transconductance and drain resistance R d. We also select the value of R O 1 and R O 2, R naught, that is 1 upon lambda I d, right, 1 upon lambda I d. Lambda is the channel length modulation parameter, I d is the drain current. So, by changing the drain current, we can change the R naught also. So, we do all these things just to get the desirable gain. As far as voltage buffer is concerned, so to design voltage buffer, we can use the common drain amplifier. Common drain amplifier means the input is applied at the gate terminal and the output is taken from the source terminal. This is the source resistance R s, this is supply voltage V d d, right. This is the common drain amplifier. It acts as a voltage buffer because the voltage gain is approximately 1. If we calculate the output resistance of this circuit, it is approximately equal to 1 by G m. So, the output resistance of the voltage buffer, it should be minimum. So, to make it minimum, we accordingly we select the value of R s and we select the value of the transconductance of this transistor M 1, fine. So, this is the voltage buffer circuit that we in general connect at the output of the operational amplifier to handle the loading effect, to avoid the signal loss, fine. Now, coming to the next topic, that is the frequency compensation. Basically, frequency compensation is used to stabilize the circuit. Like in the last class, I had discussed the concept of stability. There I had discussed that for the circuit to be stable, the gain margin and phase margin should be stable. To make it stable, we use frequency compensation. One of the frequency compensation technique is the Miller compensation, right. So, how we stabilize the circuit? The basic idea is that, let us see, let us understand it. Let us consider the example of two stage amplifier, and the gain of the first stage is A V 1, gain of the second stage is, let us say it is A V 2, right. This is V in, this is V naught. Now, let us consider that this two stage amplifier is not stable. It is not stable, it means that that dominant pole, it is away from the origin, right, away from the origin, because when we plot the gain response, let us say this gain, this is the gain response. So, when the first pole comes, then due to that pole we get the slope of minus 20 dB per decade, minus 20 dB per decade, right. And we know that for the circuit to be stable, the gain crossover frequency, it should be less than the phase crossover frequency. So, it means that the first pole that is nearest to the origin, that is called dominant pole, it should move towards the origin, and the second pole, that is the first non-dominant pole, it should move away from the origin. To achieve it, what we do? We connect a capacitor between the output and the input of the second stage. Let us see, this is the capacitor C c, that is the compensation capacitor. Now, what is the role of this capacitor? The role of this capacitor is that due to this capacitor, it exhibits Miller compensation. See, I have discussed this point, Miller effect, Miller multiplier, in the high frequency response of the common drain amplifier, sorry, common source amplifier, right. So, in case of Miller compensation, due to this compensation capacitor, the total capacitance at the input of the second stage, it increases. Let us say the output resistance of the first stage is R out 1. So, the dominant pole that will occur at the output of the first stage, it will be equal to the dominant pole frequency, it will be equal to 1 upon R out 1 R out 1 is the output resistance of the first stage, and after that multiplied by the total capacitance at node, let us say this node is A. The total capacitance, it will be equal to 1 plus AV2, the gain of the second stage, into Cc plus Ca. Now, what is this Ca? This Ca is the capacitance at node A before the addition of this compensation capacitor Cc. So, the point is that when we connect this compensation capacitor Cc in the second stage, in between the output and the input of the second stage, then the total capacitance at the node A, it increases by the amount 1 plus AV2, right. So, we had done this derivation also in that high frequency response of the common source amplifier, right. There we were getting 1 plus GMRL dash factor, that GMRL dash is the voltage gain, and that voltage gain here is AV2, that AV2 is the gain of the voltage gain of the second stage. So, the point is that due to Miller compensation, the total capacitance at node A increases, that is the result of this frequency, this Miller compensation. Now, how it is going to stabilize, the 2 stage amplifier or 3 stage amplifier or 4 stage amplifier, that we will see in the next class. So, in this class I have discussed about the op-amp design and the basics of frequency compensation and Miller compensation. This is the reference. Thank you.